So engineering 12, how are we going to calculate the work done in a thermal cycle? All right, so we're going to start taking a look at these cycles and applying our knowledge of the 4 different types of transitions that were presented in the last little video, okay? So I presented this as just a classic example of the thermal transitions that occur in a piston doing work. Okay, the gas is heated, gas expands, pressure times volume is my change in work that occurs, okay, and then the system has to reset back to the beginning, so energy has to be pulled out of the system, or heat has to be pulled out in order for it to reset, okay? So if I was to graph the pressure and volume as the system is going, we get transitions that look like this. So there's about 4 different stages. Here's an example of one of many different types of transitions that would occur. Let's say we started at point A, the system is hot, okay, and then it starts to thermally expand. The area under that graph over here would have been the work done during that isothermal expansion. Okay, so this region here is on an isotherm. Okay, so that's an isothermal expansion. And according to this system, as soon as it reaches point B, expanded to point B, it immediately cools, all right, and drops its pressure without changing its volume. So that's some type of venting situation that's occurring. And what type of transition is that? If it's not changing volume, that is an isochoric transition. Okay, and as the system is going back on another isotherm, that would be an isothermal contraction. Okay, or a compression, isothermal compression or a contraction. And then from here, the system is then gaining heat rapidly, all right, without changing its volume. So maybe some type of ignition that happened inside of the piston to go from one pressure to the other pressure, and that is an isochoric process. So within that graph, we have 4 different transitions. And in each of those transitions, we should be able to calculate either the work being done or the work done on the system, okay? And if you subtract the two, you would find the total area within that curve, which is the actual useful work being done by the piston, okay? So the total work being done minus the work being done on minus the work being done to reset the system would give me the useful work being done by the system. So as we look at these graphs, we can start to piece together how would I design an engine that would be as efficient or as powerful as possible. What we want to do is we want to maximize the area within here, okay? So there's problems in transitions that kind of look like this, in the fact that you have to lose a lot of heat very rapidly, so you'll be venting the system to create that. And we're going to see later on, how can we trick this system to maximize the area? So an example here, instead of following an isothermal down, maybe we can try to trick the system so that it flattens the, oh, I hate using that term flatten the curve right now, but it flattens the curve like this, goes over here, all right, and then that would give me an extra bit of area, which would give me a little bit of extra push and a little bit of extra work being done. So what kind of transition is here? Instead of an isothermal expansion, we have an isobaric expansion. Okay, now that would require that the system somehow maintains the pressure of the gas inside the cylinder and causes it to rapidly expand while maintaining the pressure of the gas in here to get to point B. Okay, so then I'd have a little bit of extra area. And then again, we have some venting going on, which would cause an isochoric transition, all right, and then isothermal cooling, and then another isochoric transition here. So in here, I could imagine that the system is compressing and heating as maybe like some gas or fumes are put in there, and then we get an ignition chemical reaction that produces extra gas particles and then maintains the pressure. Okay, a lot of heat is coming out, maintains the pressure as that piston is expanding to point B. Then I can somehow get some extra volume over there, like that motorcycle just driving by. Okay, so if we take a look over here, that's what engineers are trying to do when they're looking at a heat engine, such as this, like a piston. They want to find a way to maximize the area under that curve by designing interesting designs inside of the piston. So how can we do that? All right. So what I gave you in homework is a bunch of problems to calculate the energy involved in each of these types of transitions. Okay, in order to piece this together, we need to be able to calculate the energy involved in that, the energy involved in that. And that's not just the energy, it's the work or the heat, okay, or the change in internal energy. We need to tabulate all that over here. And for those of you in chemistry, this kind of is reminiscent of Hess's law, where you have a circuit or a pathway that you have to follow and add and subtract things to find the total energy change. That's my analogy between chemistry and physics in this example. Okay, so here's an example where we're just going to look at one transition, an isothermal transition, and see how we can do some calculations with it. So they told me that 25 cubic centimeters of ideal gas at a pressure of 2.5 times 10 to the 5 pascals and a temperature of 300 Kelvin has its thermodynamic state changed so that its pressure becomes 1 times 10 to the 5 pascals. If the process is conducted isothermally, that's that, calculate the final volume of the gas, okay? Well, because it's an isothermal process, this follows your standard state equation PV equals nRT, the stuff that we did in chapter 3. So in that case, it's pretty simple. I'm not going to have a change in internal energy. If I don't have a change in internal energy, I maintain the state of the gas, and I could use PV equals nRT equations. P1V1 is equal to P2V2. All right, I'll be able to just rearrange it to calculate what the final volume would be. Okay, I'm not going to substitute any of these numbers here just for the sake of time. But then I just go back and start substituting the numbers that are in the problem. I don't need the temperature. I just need the pressure and the volume. Now remember, this is cubic centimeters, right? So I got to convert that into cubic meters, unless I want my answer to be in cubic centimeters. So just to get you thinking about those kind of things. All right, now how would I go about calculating the work done in that transition? Remember, the work would be the entire area under that curve. And this is a little bit complicated because it's not a linear, it's not an easy object to be able to calculate the area under that curve. So what we'd have to do is we would have to get the integral, okay, under here. All right, so we'd have to use a little bit of calculus. And that's kind of beyond the scope of this class, but in engineering physics at university, you'll be able to derive this relationship using calculus, the integral of that graph. Okay, and then the equation for that, the work is equal to nRT, okay, the initial internal energy, times ln V2 over V1, okay? And that would map out the total area under that graph, all right? And all that information is given to you in the problem, all right? N, I would have to work out, assuming that this is an ideal gas, I can use the volume and the mole and the standard volume per mole, how many moles per 24 liters or something like that, be able to calculate the moles. Okay, and then the last question would be how much heat is transferred in that process. Then we'd have to use the first law of thermodynamics to figure things out. So here's the equation for first law of thermodynamics. Okay, because it's an isothermal process, my change in internal energy is going to be 0. All right, and then that turns this equation into something pretty simple, that the change in work of the system is going to be equal to the change in Q. Now, because the work here is positive, that means that heat had to flow through my system to do work. All right, so the change in work is the exact amount in change in Q, and that would have been heat that has been removed from the gas that was given to it by a candle or some type of reaction. Okay, so that's how we do our calculations for isothermal processes. You'll notice that in the questions I give you, they probably just give you that value. They say that the work or the heat absorbed, that the heat absorbed during that process is X amount of joules. Well, that heat absorbed is equal to the work being done. So you'll be able to use those values. You don't have to do this calculus stuff. Okay, then let's talk about a different type of expansion. Instead of isothermal, what happens if it's adiabatic? Okay, now what adiabatic means, if you watched the last video, means that no heat can be transferred in or out of the system. Okay, that system is closed to the environment, it's perfectly insulated. So when you have an adiabatic expansion, all right, the gas is stealing internal energy. The internal energy of the system is doing work to make that gas expand, okay? So then because internal energy is doing the work, the temperature drops. Now that's a pretty cool way to make something change temperatures without losing heat to the environment. So in an adiabatic process, we're storing all the energy that we have inside of that piston and making it do useful work, okay? Now, this graph is a little bit more complicated, okay? So to be able to calculate the new volume, okay, it's not your simple P1V1. Remember, I introduced these equations for adiabatic expansions. P1 V1 to the power of 5/3 is equal to P2 V2 to the power of 5/3. So if I had the pressure at these 2 points and my initial volume, I would be able to calculate my final volume. If I know my volumes, I can also then calculate the temperature of the isotherms using this relationship. T1 V1 to the power of 2/3 is equal to T2 V2 to the power of 2/3. All right, and so you can see stepwise I can do this process where I can calculate V2 in order to calculate T2. Now, why would I need those values? Well, I can use that to calculate my change in internal energy, which would allow me to calculate the area under that graph, which would give me the work done, okay? So to calculate the amount of work performed, all right, I can look at the first law of thermodynamics. Because the change in heat energy in an adiabatic process is 0, my change in internal energy is equal to negative of my change in work, okay? And then what I can do here is I can calculate my change in internal energy by plugging in the values that I measured here. Okay, so either this one or this one, and then I'd be able to calculate my change in internal energy, and then that would be negative work. So whenever you have an expansion process, my work is actually going to be positive. Okay, even though my delta U is negative, all right, then my work is going to be positive because it's expanding. All right, so that's that. So you can come back to this if you have to apply it in any of your problems. Now, I want to go to the simpler stuff, which was to calculate changes in internal energy, work, and heat energy in isobaric and isochoric processes. Okay, so here is the other 2 transitions. This is an isobaric process where my gas and piston goes at a constant pressure from one point to another. So that would go from one isotherm to another isotherm, okay? And the work would be easy to calculate. You just have to calculate the area under that rectangle, okay? So let's just look at the first law of thermodynamics. And for this process to happen, I'm changing temperature. If I'm changing temperature, the internal energy has to increase, okay? If I'm changing temperature, definitely heat had to be put in the system to do that, okay? Well, that's not necessarily true, but in this case, definitely heat is going to be put in to the system to be able to do that, okay? And then I have my change in work, and my work is going to be positive because I'm expanding, okay? So all those values are positive. To calculate work, that's simple. Pressure times the change in volume, as we've shown in a last video, would allow us to calculate work. The change in internal energy is also easy to calculate using this formula, the change in temperature. And then from that, I'd be able to calculate exactly how much heat has been put into the system to make it do what it just did, okay? And that would be this. So that would have to go from a very hot engine, okay? Some heat, like I said, with some fuel burning inside of the piston. It has to absorb heat, in a little bit more heat than the work that it's doing, because it's doing work in addition to changing the internal energy of the gas. Okay, the next and last transition that we're going to look at is an isochoric transition, okay, where the volume doesn't change. Sorry, I didn't write isochoric, but the volume doesn't change. Okay, now in that case, I'm just going to write that so we don't lose it. Isochoric, okay? So in that case, all right, the gas is starting here at a colder temperature. Something happens where it immediately absorbs a lot of heat and then changes to a higher temperature without the pressure changing. So you can imagine some type of explosion, or maybe a lot of work being done from the outside, or heat being funneled in really, really quickly, a hot gas. Okay, so that immediately the system goes up in that contained volume. The pressure is going to go up very rapidly to another isotherm. Okay, so in that case, how would I calculate the heat, the internal energy, and the work? Well, first law of thermodynamics, because the volume didn't change, my change in work is 0. That means my change in internal energy is going to be equal in that situation to the exact amount of heat that I put in. So my change in internal energy is 3/2 nR T2 minus T1, that classic formula for the change in internal energy. And that would give me the amount of heat that was put in, okay, or somehow funneled into the system from here to here to make it jump vertically like that, okay? So going back to this original graph, okay, all this would be work done by the system. Actually, this here would be the work done by the system. There's no work happening over here. It's just dropping, so it's immediately cooling, okay? And then this would be like energy degradation, where that heat is coming out of the system and then heat is being put into the system from the environment. So it's being loaded up. All right. So there would be, that area minus this area here. Well, that full area minus that area here would be the useful work. Okay, sometimes they'll give you areas of boxes and you have to just put it together. Okay, and then the last thing that we're going to talk about is just a theoretical ultimate heat engine, which I'm going to focus on just solely in the next video, called the Carnot cycle. And I just wanted to present it now before we do it in detail in the next cycle. Okay, so here is a proposed heat engine cycle. It doesn't really happen. We try to approach it in nature, where we want to try to maximize the energy that inside of the system. We want to make sure that that energy is being put into useful work and we're not degrading a lot of energy. So it would use adiabatic type of processes where there would be very insulated walls, okay, so that heat would be contained, okay? And then the other thing that we'd be using is the fact that this piston is going to have some inertia when it's moving, okay? With that inertia, I can cause adiabatic expansion and adiabatic compression processes, okay? So I can be changing the internal energy without funneling heat in and out of the system. That would maximize these jumps over here to try to maximize the area. You notice it's not a straight up and down, it's a curvy up and down. We try to maximize the area under that diamond shape if we can, okay? So what's happening in this process is first I had a gas. The gas is being compressed by a piston that's already in motion. Imagine that it has a big like, flywheel that has inertia that's pushing. There's a lot of weight on it. So the piston's already in motion and it's pushing the gas down. In that case, that would appear right over here. That would be an adiabatic compression. And then what's happening in the adiabatic compression is work is being done from the environment on the system to heat it. No heat is going in, but work is being done by the environment to heat it. Okay, so that really spikes it up to a higher temperature. Okay, and then at that point, from that higher temperature, heat is going to be funneled in from a hot reservoir. Now that's more likely like fuel igniting inside of the piston, okay, is adding heat, and that would cause an isothermal expansion. So that's like a lot of area under the graph over there, a lot higher area than if it went from over here. So we got a lot of area under that graph to do work. And then as it's in the upstroke, because that explosion, it's rapidly moving that piston up, that piston and the flywheel is going to have inertia, and it's going to keep on expanding even though we're not putting heat in there, which causes an adiabatic expansion. And that adiabatic expansion results in changing the internal energy of the piston, which internally cools it. Okay, I'm not losing heat, I'm not venting it. Okay, and then from here, we will be doing an isothermal cooling back to the original state. Okay, back to that, the original state where it's compressing. To allow the piston to fall rapidly, heat has to be pulled out of the system. Okay, so there'll be a little bit of venting and injection of a colder gas in here so that it would rapidly fall back down and up and down, up and down. Okay, so that's called a Carnot cycle. And we have to be able to calculate the energy in that Carnot cycle in a couple different ways. So here's just another description of what's happening. Okay, heat is flowing in that isotherm. Okay, we had that adiabatic compression and heat flowing in. Okay, and then we have the adiabatic expansion and then heat coming out. Okay, being venting or going to the cold sink. Okay, and then the difference in that heat, the heat coming in minus the heat coming out, really gives us an idea about the amount of work that we're going to be doing in our system. Okay, that's a classic Carnot heat engine expression. All right, and here's just another picture of the process actually occurring in the piston engine. So where we would usually start from is that point A, your compression, then your ignition, okay? And as it's igniting, it's doing a power stroke to throw that piston down. And then we have that adiabatic expansion occurring at the same time. And then we have our isothermal compression here where it's going to be exhausting and intaking at the same time to do the whole process over and over and over again. So thanks to that Carnot cycle, most of our combustion engines have been theoretically designed.